There we go. Good morning, everyone. Hope you all had a productive and valuable day yesterday with all the talks and the exhibits. Today we'll be following, and I hope you had a enjoyable but not too strenuous evening reception as well. I think we're missing a few people. Maybe they had a bit too much fun last night. So we're going to kick off this morning's sessions. If we look at the day overall, it's fairly similar to yesterday. We'll have a couple of breaks in the morning. Lunch today will also be in that same area that we had lunch yesterday. Probably go a little bit faster. We have bento boxes today, so it's easier to pick up instead of going through the buffet line. We encourage you to visit the exhibitors a bit more. They'll be there until about 3:30 this afternoon, because after the afternoon break, they'll probably start breaking down their setup. So please do try to get there no later than the afternoon break. And I wanted to mention Intrepid over in room 411 still has the Plugfest set up, so feel free to visit the Plugfest and see how you might participate in that. One other announcement, a number of people have asked questions about access to the presentation material. We do have to go through everything. There were a lot of last-minute changes and slides, so we just want to make sure we have all the correct final presentations that you've seen. And we will have those posted onto the website where you registered for the conference. So we expect those will be on the website in December once the conference steering committee approves all the final versions of them. So look for that in December, and for all registered attendees, we will send an email out to you to let you know when they are available via the website. So I think that was all the announcements for this morning, so I think I will turn it over, and we will start out today's sessions. Thank you.
Okay, good morning, everyone. Today is day 2. I would like to welcome back you all. Today we have 10 presentations in 4 sessions. I'm sorry, I'm Hideki Goto from Toyota Motor Corporation. I'm a moderator of the first half of this morning session. Okay. Let me introduce the first presentation. And the first session is network and architecture. We have one presentation in this session. The title is Automotive SDN Prototype and Use Cases. The speakers are Hyun, Taek from LG Electronics and Kilho Lee from Soongsil University. Okay, welcome.
Thank you. So I know that it's very hard to pronounce my name. Yeah. It's Hyun Taek Hong, so everybody's calling me just HD. Yeah, it's nice meeting you. So I'm Hyun Taek Hong from LG Electronics. I'm in charge of the software architecture design team. So we are interested on the architecture things these days. So the title for today is Automotive SDN Prototype and Use Cases. Thanks to the Jasper team, you remember the first session yesterday about the SDN. So they defined very well about the considerations about the automotive SDN. In this presentation, we've identified the background and SDN needs a little bit. And after that, we're going to explain some use cases and some experiments, what we did. Okay, the agenda is the introduction and some use cases. We're gonna present some kind of a reference architecture. And after that, we're gonna show some experimentation results, which shows we need to do a lot to achieve this automotive SDN. Okay, so as you may very well aware, the vehicle network architecture trends and future roadmap is dramatically changing from the domain architecture to the zonal architecture. But as we discussed on the panel session yesterday, so we also, yeah, it's true that we can implement the SDV on the domain-based architecture, but we need to think about the efficiency and the purpose. So while changing this vehicle architecture, so we need to consider the high bandwidth and Ethernet backbone among ECUs and heterogeneous network around zone ECUs. So the further consideration of future vehicle network, we identified 3 items. The first one is failover, and the second one is dynamic bandwidth control, and the third one is flexibility of future network capability. So the SDN can be a solution for these 3 identified items. So key characteristics of SDN is the first one is SDN can provide a failover operation in case of failure. As you can see here, so when we have a link fault in number 1 case, if the SDN controller inside of HPC can detect this fault and can make this alternative path by measuring the QoS and the possibilities and some kind of measures based on that. And the second one is SDN can control bandwidth dynamically based on the vehicle situation. So we all believe that SDV is aimed for the additional services after SOP. So we are 100% sure that all the network capabilities are fixed at the SOP timeline. So after the launch, we are keep updating our services on the vehicle. So based on that, we need to follow the network bandwidth changes like that. So we can achieve that by changing the network configurations, but we need to add more. We need to react more actively based on the use cases and scenarios. So that's depicted this kind of flow control and bandwidth control things. That's the second one. And the third one is SDN can reconfigure the network after the new service is deployed. Yeah, that's what I've explained. So we're going to have new applications while the vehicle is moving around on the real load. SDN in general. Traditional network is the control panel and control plane and data plane is combined together on a switch level, as depicted here. So these red rectangles are showing the control plane. So on the SDN network, so we can just gather all the control planes into one place. So-called SDN controller is in charge of this control plane. So there are various aspects of this approach. So as you can see here, so control plane can enable the centralized software control and global view of the network. So one of the presentation yesterday depicted that the SDN can make some kind of standard approach among the various vendors because the control is on a single position. So among different vendors, we need to follow these unified controls. And the data plane point of view, the control by software-based control, software control applications. Sorry, and it's also programmable. So there are a few SDN protocols ongoing for the data center services. So the most famous one is OpenFlow, but we are not sure yet the OpenFlow is fit to the automotive SDN cases. So that's why we are experimenting this protocol for this presentation. So OpenFlow, and the other protocol is NetConf, which can be used for the bandwidth control, the control network configurations. So the SDN, an alternative to the traditional switch-based network, and centralized control and programmability is the benefit of this SDN technology. And we've summarized the 5 aspects of the considerations for the automotive SDN. The first one is the automotive network is relatively small compared with traditional data center. So number of network nodes and end-to-end communications are very small. Like when we think about the gigantic data center framework, that is very huge. So At this point of view, we can think about some kind of reduced use cases and reduced protocols for the automotive cases to aim for the real-time responsibilities. And the second one is hardware upgrade is limited. Yes, it's true, definitely we can update hardware after the vehicle launch, after the SOP. But once the vehicle is delivered to the customer, it's very hard to update that. So some of the OEMs are approaching some kind of lag type approaches so that we can easily upgrade our hardware after the vehicle launch. So imagine that after the hardware upgrade is done, we need to reconfigure all the network capabilities based on the performance and the traffic flows. And the third one is the possibility of physical damage is higher than the legacy IT system. You know, that we are on the road and the crash possibility is very high. Crash can be happening a lot compared with traditional systems. The fourth one is coexistence with a legacy network like CAN. So on the panel discussion yesterday, we discussed about the CAN and legacy network. Yes, I agree that we somehow, for some time, we need to be with the legacy network traffic so that we can keep our previous legacy ECUs on the real ECU, real vehicle. And the fifth one is energy efficient network management at the minimal network operation according to the given situation. As Jasper team explained, when we are on parking stage, we need to just set up the minimum network components based on the scenario. Okay, we've prepared two video clips, which is very short. These two are our previous research about the SDN for the automotive. So the first one is mixed criticality SDN, network flows with different levels of criticality. Dynamic scheduling policy depending on the system modes. So would you please click the play button on the left side? Yeah, we just depicted this kind of four elements among switches. Just press play button. Okay, thank you. So we assume that these two kind of traffics are ongoing, which is static system, so low sensing rate on the brake system. Yeah, it's crashed. So after that, we just assume that we just decided to just stop this low priority traffics when emergency sensing rate is detected. So this high sensing rate is prompt the braking as possible. So you can stop right away. Yeah, that's the first one. And the second one is FRSDN, fault resilient SDN. So this recover from link failure by finding alternative routes. Perform path restoration from SDN controller driven to switch driven so that we can have a real-time response for the use case. Would you click the next play button? Yep. So adaptive cruise control, we assume that the left vehicle, you will see the screen from the left vehicle. So standard SDN, so control driven, will follow. And failure occurred, they crashed. But by moving this control logic from SDN controller to switch, we can have more fast response. Fault occurred, even though fault occurred, we can find the alternative paths right away. Yeah, that's our previous research. You can find the full version of these two clips on the YouTube website. And so I will present the three use cases for the SDN cases. The first one is dynamic bandwidth control. The scenario is a reserve bandwidth to front camera sensors when emergency event is detected. You can imagine that. I think I'm running out of time, so I want to be very quick. So bandwidth and priority controls, queue management is needed. And the second use case is CAN signal transfer with priority. So we may have these CAN ECUs connected through the zonal ECUs. So while transferring this signal to service so that we can send messages from CAN to the Ethernet traffic. So while transferring that, we can think about the priority controls. Select a relevant priority when transferring, and the second one is transfer frequency control. So, the CAN messages keep coming, so we need to control the frequency of the packet messages. And packet size control is also possible. We can just combine some CAN messages into one Ethernet frame. And the third one is maintain reliable communication, which is similar, I've already explained. From next session, I will introduce Professor Lee, who's the expert of the Automotive SDN. Thank you.
Okay, thank you for the introduction. From now on, let me take over the presentation. I'm Kilho Lee from Soongsil University, South Korea. And I will cover the technical details of our work. We are now developing on a reference SDN architecture. Next one. So we are now developing this kind of reference automotive SDN architecture. This is the proposed architecture. We consider the zonal network, which consists of number of zonal gateways and central computing units, like this. And they are connected to each other through Ethernet links. And there are some devices and ECUs connected to each gateway through Ethernet link. And also, there are some devices can be connected to the CAN buses. In this architecture, to make software-defined networking, each zonal gateways and the central computing unit works as SDN switches, and the central computing unit works as a SDN controller. The right side figure shows the overall architecture of the typical SDN structure. It defines data plane and the control plane with 3 different layers, like infrastructure and control and application layers. In our architecture, each zonal gateway and the central computing unit works as data plane, and the central computing unit also contains this control plane. So the key component of our reference architecture is the network planner. The role of network planner is to monitor and maintain the global network information and to reserve the bandwidth for a specific flow, and then to reconfigure the path when some fault happens. To do this, the network planner should be able to dynamically control the bandwidth reservation and packet prioritization, and it should maintain the reliable communication with runtime fault recovery mechanisms. Now, let me cover the details of each feature. The first feature of our architecture is routing for runtime bandwidth reservation. When, as you can see in this figure, when a vehicle application wants to transmit some traffic, it first asks the network planner to make a reserved bandwidth path on the network. So when this routing request is made, then the planner conducts some bandwidth-aware routing based on this global network information. And when it finds some proper route in the network, it then deploys new packet forwarding rules to each switch to make a bandwidth reserve on each link. So we consider these kind of issues to make this component. The first one, it should be responsive, and it should handle QoS or timing requirements, and it should be runtime dynamic. The next feature is fault handling. When some fault happens on nodes or links, then the planner should detect that fault, and it should change the paths of all affected flows by that fault. So to do this, when a port is detected, it then updates its global network information And then it distinguishes affected flows by that port, and then recalculate the passes of that affected flows, and then deploy new packet forwarding rules to each switch to avoid the link, to avoid the port. The last feature is signal to service translator to support the legacy communication. In some cases, CAN signals can be transmitted between gateways. To support this, signal to service translator translate CAN signals into service packets and also vice versa. To do this, we consider these kind of issues, how to control the priority of the CAN signals, and some filtering may be required while translating from signals to service, and how to integrate this feature into the current service-oriented architecture. Here is our prototype. We made this kind of prototype, which consists of a number of embedded computers, as shown in this figure. Each embedded computer works as a zonal gateway or central computing unit or some devices, and they are connected through the physical Ethernet links. And some of gateways also has CAN interfaces, like this. This kind of gateway is also connected to the CAN buses, and some other CAN devices are also connected to that bus. So this is our prototype implementation. And we did some experiment on top of that prototype implementation. The first evaluation is to show the effectiveness of bandwidth reservation. We have two pros in this setup. First one is the target, which is safety critical, and it may require some certain amount of bandwidth. And the other one is background, which is best effort. As you can see in this figure, somehow both pros share some link, like in here. And resource contention happened in this link. So without any bandwidth reservation, when you see in this result, the throughput of the target highly decreases when the background traffic is generated. But when we apply SDN for bandwidth reservation, then the throughput of the target is still maintained as much as it requires, regardless of the background traffic. The next evaluation is to show the effect of the CAN signal prioritization. In this setup, we also have two pros. First one is the target, which is the CAN signals with frequency of 1,000 Hertz. And the other one is background, which is also best effort. Somehow both pros share this link, and the resource contention happens again. As you can see in this graph, if there are no background traffic, then the latency of the target traffic maintains stable. As you can see in the graph, the black dots represent that. But when the background traffic is generated, then the latency of the target becomes longer and even fluctuated. When we apply SDN to make bandwidth reservation for this CAN signal, then the latency of the target flow shows very stable result, as you can see in this yellow dot in this graph. The rest evaluation is about port handling. In the middle of the data transmission, a link port happens in the data path. So the network planner detects that link port, and it changes the data path to the alternative route, and the data communication will continue through this restored route. So as you can see in the graph, in the middle of the data transmission, link port happens in here, but for a while, the data path is restored by the network planner, and then the data transmission will continue from here. Okay, so let me conclude the presentation. We propose some reference architecture of the Automotive SDN. We present some key technical issues and some use cases. And we also present some reference architecture and then give some prototype implementation and some evaluation result. So our prototype implies that SDN can provide better flexibility and better efficiency and reliability. And so we believe that these kind of features could be essential for software-defined vehicles. So we have some remaining issues such as security and functional safety, better interfaces, and the integration with the current automotive software architecture like service-oriented architecture. Okay, this is end of our presentation. Any questions?
Thank you for the great presentation. Actually, Jasper is focusing on this SDN area. So we, Jasper, would like to discuss with you, if possible. Thank you. Any questions? Please speak your name and your affiliation first, please.
Thank you for your good presentation. My name is Yoshihiro Ito. I'm from Nagoya Institute of Technology. So I have one question. Could you show me the third slide of your presentation? I think it's a third.
Third page?
Third. Okay.
Yep.
Thank you. So in this slide, you treated three features of SDN, and the first feature treats fail-safe operation.
Yes.
And in your figure, the SDN controller exists over cloud. Is it okay? SDN controller
Exists here.
here. So what is a cloud?
A cloud.
Cloud.
Yeah, just cloud means that to deploy the new application. It's not related with the in-vehicle SDN use cases. We just want to defect the new services from cloud to a vehicle.
So in the first case, so cloud does not send the control to the switches.
That's also another aspect because we can imagine that these are all also the network. So we can include these cloud components to the SDN control case. But I believe that's the next step maybe because we are not fully implement on the automotive SDN yet. So yeah, that's very good question.
Thank you. So if the SDN controller exists over the cloud, I wonder how do you solve the latency between switches and controllers?
From cloud?
Yes, but I think it's misunderstood. So
Yeah.
thank you
Okay,
very much.
so I understand your question. So maybe that's possible when we really get the 6G, maybe. So first, let's think about the in-vehicle network first, and after that, let's consider the cloud on the SDN control.
I think it will not solve problem.
Yeah.
Thank you very much.
Okay. ありがとう.
Any other questions? Please go ahead.
This is Hyun from Delta Networks. So earlier I saw the presentation on the SDN on CAN bus. Can you elaborate a little more about how you use the SDN? What's the interface you use to use the SDN control the CAN bus signal? Because the Ethernet, we understand how Ethernet been controlled, but for the CAN bus, can you elaborate a little bit more? Thank you.
Okay, so your question is, yeah, In this case, how can the SDN control the CAN traffics? Yeah. So what we've done here is you can see the S2S signal to service translator on this zonal ECU. So by getting this CAN message through the CAN bus, we are translating these signals into the service. So as I explained, while we are transferring this signal to service, there are three considerations we need to think about. Yep, those are these three components. So select a relevant priority while transferring. So whether this CAN traffic is very urgent or low priority, and that's the first one. And the second one is transfer frequency control. We cannot send all the CAN signals to the Ethernet. That's not possible. So we need to some kind of context aware, which is controlled by SDN control on the HPC. That's the second one. And the third one is packet size control. We can just combine a few CAN messages into one Ethernet frame. That kind of approach is also possible. Is this answers your question?
Yeah, earlier you mentioned about they use the OpenFlow or NetCom to control the data plane.
Yeah.
And this is still using the same?
Yeah, so since we've transferred that signal into service, we can send that package under the OpenFlow protocol.
Okay, thank you.
Okay, thank you.
Any questions?
Jasper member. I was waiting for you.
Thank you for your interesting presentation. I'm Takumi Nomura from Honda. Please go back to 15. Slide
15?
Number 15.
Yep.
I'm very interested in what kind of device you used. I believe Automotive SDN will the big issue to realize Automotive SDN, how to realize the poor CPU. So I'm interested in what device did you
Yes. Okay.
In this setup, we just choose embedded computers which equipped with ARM-based CPU. It's very low power CPU. Maybe the cost of this embedded computer is less than, say, $40 or $50. So you can make this kind of prototype implementation with very low cost ARM-based CPU like Raspberry Pi. But in this scenario, we didn't use Raspberry Pi, although we just choose Odroid, which is variant of Raspberry Pi.
Thank you.
Yeah, just for the experiment purpose. Yeah, we know that that's not enough for the Automotive SDN. Okay.
Okay. Go ahead.
Hi, I'm John Simon with Intrepid Control Systems. I was very interested with the videos that you had of your experiments, and I'm curious, did you have any problems or raised concerns between switching between the two different network configurations? Because I see a lot of analogies between that and something that's historically been a big problem in automotive ignition status. Just changing statuses has resulted in a lot of different problems. And did you have any concerns, or do you have any mitigation strategies for an orderly and deterministic switch between one network configuration and another?
Sorry, you're asking on this video use cases, you're asking any considerations while we are switching?
Yeah, reliably switching between one mode and another deterministically, not having any problems with the network ending up in an undesired state.
The main problem in that case is the latency for switching the rules, or latency between the switching the modes. So this is the first step of the prototyping of this automotive SDN systems. So we have to consider more about that latency problem in between switching the rules. And another consideration is the out of order of packet arrivals and some packet losses in between the switching cases. But I believe that when we properly address that latency problem, then that kind of problem can be mitigated. That's my opinion.
Okay, thank you.
Okay, it's behind the schedule, so finished. I think Jasper would have lots of questions. Maybe.
Yeah, we can just have separate session for
Anyway, sorry. Hyun, Taek, and Kilho, thank you for a great presentation.
Okay, thank you.